All right, well, also I'm glad the mic is movable because I like walking around and I am just short enough to hide unintentionally behind the computer at the podium. So, good evening, everybody. My name is Jen Ito. I am assistant professor in the physics and engineering department at Westmont College. It is my pleasure to be here tonight with you. So, Ronnie, thank you for the invitation. And yes, tonight I'm going to be sharing with you a little bit of the work that I did in my dissertation and continue to do now still as I work at Westmont. So yes, title is Characterization and Deployment of the PolarBear 2B Receiver to Measure the Cosmic Microwave Background Polarization. Kind of a mouthful. Basically, I got to do research and development on a telescope that looks at radiation from space. But first, a little bit about me. So as Ronnie mentioned, I was born and raised in San Diego. I popped up to the Bay Area for my bachelor's and then popped back down to San Diego for my master's and PhD. Thank you, Tom. And then, yeah, currently working at Westmont College and the Westmont Observatory director. To give you a little bit of flavor of the classes that I teach and the research that I do. So I teach all the astronomy or astrophysics related courses there. So observational astronomy is a lab-based class where students get to learn how to work with the 24-inch reflector that we have on campus. It is a class that started last spring, and this is a picture of the inaugural set of students that got to take it with me. They have all since graduated and are doing great things now. So we have Natalie Fogg from the left, starting from the left. Natalie Fogg, Becca Hudson, Tasha Lowe, Jacob Nelson, and Michael Liu. I also teach, this semester I'm teaching an astrophysics class. It's an upward theory, and I've got some of my students here tonight, so thanks for the support. Yes, in my hand. So this is a class that was originally taught by Tom Whittemore, actually, and there he is. So very grateful for his help as I prep for class. I also teach Introduction to Astronomy, which is a GE class, Physics for the Life Science, which is an algebra-based physics class, and then another fun one too is Physics of Music. This is a fun combination. Let's see, Ronnie also mentioned I got married recently. It sort of reflects the marriage. So my husband is here, Dr. Daniel G., who is the conductor of the choirs at Westmont College. Yeah. And yes, as Ronnie mentioned, we got married recently, so I am still counting the months. So very grateful for Daniel's support, as today we are celebrating our 5-month anniversary. Yes, grateful for him for all his support and the work that I do. All right, research areas, cosmology, instrumentation, that's what I'm going to be talking about tonight. Another area that I am ramping up is looking at variable stars. And again, this is something that Tom did when he was at Westmont. So hoping to restart that program, working with students. And then one area that I would like to start in the near future is looking at physics education research. So one of my desires is to explore, discover, continue to learn and implement ways that we can teach physics well. So, all right, enough about me. On to the talk. Okay, so outline for tonight, going to introduce cosmology and kind of the background, the cosmic microwave background. Simon's array is the project that I work on, and then PolarBear 2B is an instrument within that project. So I was involved with assembling it, validating it in the lab, and then deploying it and commissioning it for the science work. And then I'll share a little bit about current work and future goals. So to get us started, cosmology and the cosmic microwave background, we're going to start at the beginning. That's a very good place to start. On the right side here, we've got us today at 13.8 billion years, plus or minus a couple 100 million, so give or take a few. But we've got our galaxies, stars, planets, things that we see. On the other end, over here, is a period called inflation. And if I were quick enough on my feet, I would make some sort of economics joke at that. But Inflation is a time period in astrophysics. It's a time period that describes the hyperexpansion of space. So I'll explain that a little bit later. But for now, we're going to ignore it. So pretend it's not there. Don't worry, it'll come back. But for now, it's not there. So it is thought that the beginning of the universe started as a hot, dense plasma. So it's basically a hot, dense soup of fundamental particles. After about a microsecond, the first particles such as the neutrons and protons were formed from these fundamental particles. And then 3 minutes later, you get the first nuclei. So these are your helium, hydrogen, nuclei, some lithium, but all the light elements that we're familiar with, deuterium also. And at this point, oh, I should also mention, so you might be able to see there are these little squiggles. Those represent light particles, so particles of light, also known as photons. But at this time, right, there are these nuclei forming, but there aren't any stable atoms forming. So there's no hydrogen atom, right, which is one proton and one electron, because anytime that the electron bonds to the proton, there's a photon there that knocks it away. And so you have all of these all these nuclei. But you also have then a lot of free electrons that are there. And the light then not only is, removing electrons from nuclei, but they're also scattering off of these free electrons. And that kind of scattering is called Thomson scattering. Now, my astrophysics probably know why I put Thomson scattering on their exam last week. So Thomson scattering is an important aspect in studying the CMB, which is why I mention it. But right, so yeah, you have these light particles that are scattering off of these free electrons, and there is such a high density of particles that the light doesn't get to travel very far before it collides with another particle. And so it's something that we called we describe the universe as being opaque. After some 300,000 years or so, we get to this section, this area where it's labeled first light. And that first light is referring to what we call the cosmic microwave background radiation. So at this point, the universe has expanded and cooled enough such that stable atoms can form. So you have your hydrogen atom with an electron and a proton, you have your helium atom and things like that, which means there are fewer free electrons floating around, which means that the photons can travel farther. And so that then is, I guess, the description behind how we can see the CMB now. After that, we have first stars, galaxies, dark matter, dark energy, but that stuff doesn't matter. Right, focusing on the first light part. But before I talk more about the CMB, I'm going to talk about this idea of black body radiation. And yes, as Ronnie mentioned, my favorite animal is the horse, so I got a picture of horses on here. Black body radiation is a term used to describe the radiation coming from an ideal object that absorbs all incident radiation, right? So if you have an object, it absorbs any sort of radiation that is incident upon it. It doesn't reflect any, and any radiation that comes from it is based on its own temperature, the object's temperature. And sometimes, right, objects can emit kinds of light that we can't see. There are different kinds of light. So for example, right, we all are emitting thermal radiation, right? The horses are emitting thermal radiation, and we put on special night vision goggles to be able to see that. So the type or color of light emitted directly relates to the temperature of the object. Another example of this is if you take like an iron rod and you heat it up, right? The cooler, even if, when you heat it up, it starts to glow. When it's a cooler temperature, it's more reddish orange, and then as you heat it up, it becomes more bright yellow. So it's kind of the same idea. So it was predicted that the cosmic microwave background, it is basically measuring the temperature of the universe, and it was predicted to, the light profile was predicted to represent a temperature of somewhere around 5 Kelvin. So when we actually started measuring cosmic microwave background, it turns out that the spectrum fits a black body spectrum of an object that is 2.725 Kelvin, which is pretty close, especially when we talk about, at least in astrophysics, right? Same order of magnitude. So the plot here on the top is showing the intensity of light and the wavelength along the x-axis. The dots are the data points, and then the curve is the model of the black body at 2.725 Kelvin. And you can see the dots line up pretty well with that curve. Another way to show this and represent this is the bottom in the is a plot in the bottom, which are the residuals. So this is the difference between the data and the model. So if you have data that fits the model perfectly, your residual is going to be 0. So that is that right here, the solid line there, that would be 0. If the data fit the model, then all your data points would be lined up with that 0 line. And so statistically, we have our data points here and their error bars, it best fits that 0 line. The colored lines there are other non-black body models, but the data best fits something that looks like a black body. So yeah, so this was kind of one of the big things that really got the study of cosmic microwave background going. Let's see, I mentioned inflation was going to come back. So as we were studying the CMB more and more, we noticed that there were regions of the universe that we would measure the CMB. They were regions that were far apart, but the temperature that we were measuring was the same. And this was actually a problem because even with the 13.8 billion years of the age of the universe, there wasn't enough time for those opposite ends of the universe to have become the same temperature or thermally equilibrated. So that conundrum that came up is known as the horizon problem. And so inflation was a theory that is proposed to address that. And interestingly enough, inflation was first proposed in 1981 by Alan Guth as a theory that would address a different problem that we were seeing with the model of the Big Bang. And that's this question of, with the Big Bang theory, we should be seeing more magnetic monopoles, right? So magnets, we typically think of them as having a north and south pole, but it was predicted that there should be these particles that are just north pole or just south pole, right? So magnetic monopoles. And we haven't found any yet. So the theory of inflation was developed to try and address that. Turns out that it could also address this horizon problem. So the thinking is that if you have the universe that has begun, and when it starts, it is in thermal equilibrium. So the universe is all the same temperature. With inflation, then, it is the hyper expansion of space. So a way that I've heard it described is pretend you're sitting on a lake with a bunch of your buddies fishing in boats, and you're close enough with your buddies, you can see them, talk to them, whatnot. And then in less than a fraction of a second, lake expands and your buddies are so far away you can't see them anymore. So sort of like that. With the universe, it's thought that, right, the universe starts off as the same temperature, space expands and expands so fast that the temperature remains the same in all the different places. So that's conceptually how that works. So the question is, well, do we actually see evidence of inflation in the CMB? And that evidence would be from these predictions. So inflation predicts perturbations in the gravitational metric. So perturbations just means fluctuations. Gravitational metric has to do with the distribution of energy and the geometry of space. Could also think of it as it's something that describes the gravitational field. So two different kinds of perturbations here. We've got scalar perturbations, which are density perturbations. So this is shown by the top graphic here. So you've got areas of more or less gravity. And the observable evidence for this would be temperature anisotropy, so fluctuations in temperature in the CMB, and something called E-mode polarization, which I will mention a little bit more later. Another type of perturbation would be caused by gravitational waves. So these are gravitational waves that were instigated by inflation. Sometimes you'll hear it called as the primordial gravitational waves. And the observable evidence for this would be a different kind of polarization in the CMB, namely B-mode polarization. So these are the 3 boxes to check. Let's see if we check them. All right. So let's say we take view of the entire sky around us. What's the word? Put it down onto a 2D map, project it onto a 2D map. And let's say we could actually see the kind of radiation that the cosmic microwave background is. My artist rendition of what that would look like is this kind of orange-brown color, and it would be basically uniform all around. So yeah, average temperature here, 2.725 Kelvin. If we were to subtract this average, what we would get is actually the pretty picture that we're all more familiar with when we talk about the CMB. So this is actually looking at different temperature fluctuations within the measured CMB. You can see the temperature scale on the bottom. And so you have these variations between the redder and the bluer spots. Now, we can take this map, do something called a Fourier transform, and convert it into what's called a temperature power spectrum. So this is telling us how the temperature varies across different angular sizes on the sky, or angular scales on the sky. So if you have here, if you have a higher number, that means you have higher temperature variations for this size patch on the sky. So in these units, a lower L is actually means you're looking at a larger patch on the sky, and higher L means that you're looking at a smaller patch on the sky. And yeah, so we do see these temperature fluctuations. And so we have our first one checked off here with the C. So we do see the CMB temperature anisotropies. All right, second.
So what distance does that peak correspond to?
Oh, right, so the peak, good question. So let's see, an L of, I think, let's see, this is 100, no, this one's 400. So this peak corresponds to a scale that is smaller than the angle of the moon, 350. Thank you. So the moon is roughly 400. So if you were to think of the angular size of the moon on the sky, that is roughly 400, and so it is something a little bit smaller. So 350.
Oh, it's not a distance; it's an angle.
Oh, yeah, it's an angle on the sky. Yes.
Got it.
Yes. No, sorry about that. Thanks. All right. So so next is the E-mode polarization. So polarization is basically, you can think of it as directionality of light. So this is the same idea as with like polarized sunglasses or polarized glasses that you use for 3D movies. And there are 2 different kinds of polarization. So you have linear polarization, you have circular polarization. Within linear polarization, you have this what's called E-mode and B-mode polarization. And so the evidence would be to see the E-mode polarization, and for the sake of brevity, we do. This has been studied for over the last decade, and it's pretty well established that we see the signal. All right, so then on to the B-mode polarization, and this is the big thing that current cosmology instruments are looking for, because this is what we have not found yet. There are 2 kinds of B-mode polarization. There is one that happens from gravitational lensing, and there's one that is sometimes called primordial B-mode polarization, which is what this one would be considered. So we're looking for this primordial B mode polarization. So that is where the Simons array comes in. Simons array, so it is, if you go onto Google Maps and look up Simons array Chile or PolarBear Simons array, you will find this in the northern part of Chile in the Atacama Desert. The site is at an altitude of 5,200 meters or 17,000 feet. Yeah, we have half an atmosphere up there, so yeah, we do try to wear oxygen. The reason why we're there is because it is very dry. So, right, it's not so much because of the light pollution, because actually our telescopes don't look at the visible light. So we can actually take measurements during the day. But because we're in millimeter wavelength light, it actually depends on how much moisture is in the air, because the moisture, the water, can actually emit signals in the millimeter wavelength, and so then contaminate our signal from the CMB. We use a measurement called precipitable water vapor. So this is basically if you take a column of water, a column of atmosphere, how much water is in that column. This is a plot of transmission versus frequency. The CMB peaks at a frequency of 150 gigahertz. So from this plot, then we can see that there are kind of these two windows that we could measure the CMB in, where the transmission doesn't vary too much with the PWV value. Yeah, transmission of 1, so meaning that the CMB can come all the way through, is at the top. And so we picked these two windows to design our detectors, with. This is an aerial shot of the site. So Simons array is the 3 telescopes that are situated here. And then next to us, we have other neighbors, other cosmological projects who are also studying the CMB and have done a lot of really amazing things. We have the Atacama Cosmology Telescope, or ACT. Class is here, and I'm sorry, I forget what that acronym is. And then we have a new one. This is a slightly older picture. There's a lot more telescopes here now. But that is a site called Simons Observatory, connected to Simons array. So Simons array was funded by Jim Simons, and he has continued to support larger projects such as Simons Observatory. Okay, so Simons array is actually an expansion of an original project called PolarBear. PolarBear consisted of a single telescope. It was the Juan Tran telescope, had a 2.5 meter diameter primary mirror. It was an off-axis Gregorian Dragone style telescope. And it had a first generation PolarBear cryogenic receiver. So cryogenic just means we got it really cold. Receiver it just means camera, basically. So we have a really cold camera that's on there. There were roughly 1,200 detectors that were measuring just at one frequency, 150 gigahertz. So that's the bandwidth, or bandwidth centered at 150 gigahertz. And observations began in 2012, and it had 5 seasons of observations. So briefly, a couple results from those. The important phrase here is rejected no lensed B modes with 3.1 sigma confidence. And this is where sometimes I get confused with how scientists frame things, but basically this just means that we found it. So we found the B modes. That's what that means. And I should say specifically, we found the gravitationally lensed B modes. So this is not the primordial B modes that we're looking for, but we found the other kind of B modes. We were able to add our data to this plot that shows the spectrum of those lensed B modes. Unique thing about this set of results is that it was the first project to calculate lensed B modes using just CMB polarization data alone. So there are other projects, the other projects on here that did it used additional data beyond the CMB data that they were gathering. Okay, and then results from large patch. So the previous one was a small patch results. These are larger patch, so looking at a larger section on the sky. These two papers, so the second paper is just an improvement on the first with more analyzed data. And this plot is showing all the systematic errors and systematic noise that were calculated for the instrument. The black line is the total. But if you look at the top, we still have statistical noise being the dominant factor. And so one of the ways to lower your statistical noise is to increase the number of detectors that you have. And so that's where Simon's array came in. So it's an expansion of the PolarBear project in order to increase our sensitivity. So there were two additional identical telescopes that were added. Up here, we have the PB2A, so PolarBear 2A receiver, so it's second generation, hence the 2. So PB2A receiver in the Nicholas Simons telescope, and then we have PB2B in the Paul Simons telescope. And you can see too, we have this 90/150 gigahertz. So these receivers had detectors that could measure in both of the bandwidths that I mentioned earlier. All right, the last published science goals were to continue measuring the gravitationally lensed B modes. So this will give us new information about studying the matter distribution and constraints on neutrino masses. And then to, still try and detect the primordial B modes. Like any good story though, plot twist. Based on our instruments' capabilities in the field, we are doing something slightly different. And so, also part of working on science projects, you design things the best that you can, and then you do the best that you can with what you end up with. So we are shifting and still measuring the polarization of the CMB, but shifting it to measuring circular polarization, which is another area that is less studied, I would say. So that's kind of it's an exciting thing, but also a shift from what we were originally planning. But still, it was really neat and great to be able to work on this project and work on this receiver. So PolarBear 2B is a very special one for me because I spent a lot of time with it. Spent a lot of time in the lab, did the final in-lab characterization before deployment, went with it down to Chile, built it there, and helped put it on the help get it ready to be able to put on the telescope. So just some, there we go. Okay. So first a cross-section of the telescope with the receiver. So I have a drawing here on the left. So we have a primary mirror, 2.5 meters in diameter. That goes to a secondary mirror here, it's 1.3 meters. And then this boxed part here is the camera, so the receiver. And then I have a picture of the last time I was down at the site with a couple of my research students from Westmont. So we have Michael Liu and Jacob Nelson, and they came with me to do some work that I will show pictures of later on. And I'm going to see if this video link works. And you can see a little bit of the telescope in motion. So this is looking from the bottom. This is the receiver here. It's about 7 feet long to give you scale. And then secondary, and then we call these saddlebags because they're like saddlebags that are hanging on either side. Those have all the readout electronics and other control electronics that we use. So. All right, so now just for some highlights from receiver assembly. So one of them is assembling the focal plane. This was tedious and meticulous, but I actually really enjoyed it. And then also had to do measurements to make sure that these detectors actually work the way that we designed them to, right? So these detectors were designed and built at Berkeley, and then we tested them inside PolarBear 2B. And then I also was part of the team. I led the group that did the fully integrated receiver validation right before we deployed. All right, so this is a picture of me with a I should say mostly assembled PolarBear 2B at the site. Gives you a sense of scale, right? So I said the cylindrical part is roughly 7 feet long. Inside here is roughly 3 feet across. There's a box in the back that is roughly 4 feet by 5 feet. And so it's shaped like a large DSLR camera, if you're familiar with those. This is a cross-section drawing of it. So if you were to remove all the lenses inside, I could fit inside of there. And I did have to, well, I had to fit inside the box once. So just give you another sense of scale. Starting from the right, we have our window. Goes to what we call a half-wave plate. So this is a frequency modulator. It was a really cool piece of technology that was developed for this project. And it's a plate of sapphire that utilizes superconductivity and levitates. So it's freely spinning. So it's really cool. We have 3 re-imaging lenses, a Leo stop, and then in the back end area here, back end aperture. So this is the joint between the lens section and then our detector and readout. So we have our focal plane here and then a bunch of cryogenic readout. If you notice, I have different labels here, 4K, 50K, 300K. So all of these elements are within concentric shells of varying temperature. So whatever's inside the 4K shell is 4 Kelvin. Whatever is at the 50K shell is 50 Kelvin. 300K shell is just the room temperature. It's a vacuum sealed chamber, basically. And we break it up into calling the part with the lenses, the optics tube, and the part with the detectors and readout as the back end. I just put that up there because I will slip into that terminology and I wanted to make sure you all knew what I was talking about. Okay. So focal plane assembly. In the back end, we have a focal plane tower. This is a structure that holds all of our detector modules. In real life, it looks like this. It's about 1/2 meter across. Each of those black hexagons that you see is actually a detector module that has a detector wafer, a lenslet array with a bunch of little lenslets that focus the light onto each detector, and then some readout. If we look at an individual pixel, it's about 3 millimeters across. This is a sinuous broadband antenna. And then these shiny rectangles are our detectors. And so a receiver has roughly 7,500 detectors total.
What are the detectors made out of?
Aluminum manganese. Yeah. Yeah, I'll talk about it a little bit more, but yeah, aluminum manganese, and they are superconducting. Yeah, so. Okay, so how we assemble this, we take a detector module in its protective shipping case, we pull it out and lay out these very fragile wires. These are the wires themselves, they're wrapped in a protective tape right now, but the wires themselves are niobium titanium wires. This is the empty focal plane tower. You take each detector module, you slip it in the front, you turn a bunch of tiny, tiny screws, and you get this beautiful arrangement of hexagons. Yes, anyway, okay. So I mentioned that I did some characterization work for deployment. So the detectors that we use are called transition edge sensor bolometers. These are basically temperature varying resistors. So on the left is a circuit schematic. This is our detector. So when a photon hits it, the temperature changes, which then changes the resistance. Now I mentioned these are superconducting. And so there is this transition that happens from when it's in its normal state and it goes into its superconducting state. And so down here, the current flows freely, and up here, it's got a constant, what we call a normal resistance. So it acts like a regular resistor that is temperature independent. So the way that we utilize this technology is whenever we have a CMB photon that hits our detector, let's say we are having our detectors biased in this very small range here but it's sitting here whenever there's a change of, whenever there's a tiny change of temperature, there's a change of resistance which then means there's a change in the current that we measure. So that's how we detect the photons that hit it. Now, part of this though is that, right, if you keep having photons hitting the detector, it's going to heat it up, and then eventually it's going to make it so hot that it goes out of its transition region. So we voltage bias these detectors to have this electrothermal feedback loop to create stable detectors. So here I have an equation that has to do with power, electrical power, and we have voltage squared in the top and the resistance in the bottom. So when we voltage bias these detectors, that means we keep them at a constant voltage. And let's say we start off at this red dot here on the transition. A photon comes and hits the bolometer, heats it up. That means the temperature increases, which then moves this dot up, increases in resistance, but that increase in resistance lowers the electrical power that is on the bolometer, which then lowers the temperature, which then brings the resistance back down. And so that's the feedback loop that happens to be able to keep our bolometers in their transition range. So part of characterizing these is making sure, okay, do these have a normal resistance that we designed in? Does it have the transition temperature that we want? And so part of that is, I said one example is measuring the critical temperature of these detectors. So we defined the critical temperature as the temperature when the bolometer resistance is 80% of the normal resistance, and the target range was 420 to 470 Kelvin. The upper bound was set by detector noise properties, and the lower bound was set by the ability to cool the bolometers, right? So we only have so much power that we can use to cool these, and so we had to take that into account. And the representative sample that we had fit within that range. And so that this was part of validating the detector modules that we had, and said that they were good for deployment. All right, and then last thing with receiver assembly and validation. So I led the group that did the final run. That was a full integrated receiver run with all the optical elements and 7 detector modules. And the results was that we achieved a focal plane hold time of 2 days. So the way that we cool our detectors is by using basically evaporative cooling. So it's evaporating helium-3, helium-4. You have to recycle that to be able to keep doing this process. And so the question is, well, how long can you go before you have to recycle it? So we were able to do it for 2 days. And then the detector and readout characterization, the results were that 5 modules were chosen for deployment. The receiver requires 7, so we had 2 other ones tested at other institutions. And then it was, we were able to validate the cryomechanical operation of the cold half wave plate. Yeah, so again, this is technology that we were developing. Okay, I was gonna say something, but it's jumping ahead, so we'll save that. It's okay, it's coming. All right, so that was receiver assembly and validation. So now deployment and commissioning. So now that we figured out that our receiver basically worked, we had to break it down and pack it up and ship it off to the site. So that meant packing all the different sections. We could break it down into different sections, packed it up into a crate, and had those crates packed into a shipping container, which then we shipped down to Chile. And it took about 2 months to get there. Yeah. So there's a group of us that met it there. So here we have Calvin Tsai, Darcy Barron, Lindsay Lowry, and Dave Butker, myself there. And so we were there to meet the container, super excited, got it there, started unloading stuff, put the back end of the receiver into the high bay where we were going to start building it. But guess when this was? This was March 2020. So this is my COVID story. I was in Chile. It was at the point where the Chilean government had shut down international borders, so they weren't allowing any non-citizens in. I still vividly remember the time of thinking like, okay, do we stay here? Is it safer to stay here? Or do we actually go home? And so we did eventually decide it was better to go home. So we basically evacuated out of the country. We kind of set things up as best we could, not knowing when we would go back. But yeah, and then we got home, and I think I got home either the day before or the day of when California shut down. So that was exciting. But very gratefully.
Did you get COVID?
No.
Good.
Yes, I was thinking about that recently. I'm very surprised that I did not get COVID coming back. Very grateful for that. But gratefully, we were able to go back in March the next year in 2021. Felt really fancy and important because we had to get these like diplomatic visas to go into Chile to do this. But yeah, so anyway, it was neat to be able to go back. This is me and Lindsay, and we were building things. Turned out that the timeline for one of our optics pieces was delayed again because of COVID, so we had to build things as much as we could and then leave and come back. So we came back in June, where they had the largest snowstorm that they had had in like a decade. It was like over 6 feet of snow. It was incredible. But that meant we couldn't make it to the site. So spent 5 nice weeks in a hotel room. So, you know, if first you don't succeed, you try and try again. So we went back in August, and this is myself with Bryce, and we were able to keep building things up. Eventually we were able to finish it. And then stuff happened. It broke a little bit. So we tried again. So May 2022, another group of us from both Berkeley and UCSD. And this time we were able to build it up all the way so that we could hoist it onto the Paul Simons telescope in July of 22. And you can see our very fancy styrofoam window cover there. Make sure nothing hurts the front. All right, so commissioning status. First light was achieved in January of 23. We successfully operated the cryogenic half wave plate. So again, this is what I didn't want to say earlier because it was spoilers. But this is the first demonstration of this kind of wave plate in the field. So that's really exciting. And Bryce Bixler, who's grad student at UCSD, this was basically his baby. He knows everything about it and worked a lot of hours on it. And then we've also successfully performed calibration observations. So now what are we doing? So the last trip that I went on, I mentioned, was June of 23, and have a couple of my students pictured here. So Michael Liu and Jacob Nelson helped with a bunch of just different projects and maintenance around the site. So in the left picture, they're installing a beam for the bottom of the receiver cover. Jacob's working on a thermal calibration instrument. Michael's helping screw on the front panel of the what's it called? Receiver enclosure. So there's just a lot of maintenance work that we did around. And then with PB2B as a whole, we've been measuring the CMB over the last year. And we concluded observations this month, and actually Simon's array concluded this month as well, but we're going to continue data analysis throughout the next year. Specifically at Westmont, I'm working on it's called a telescope pointing model. So this is part of the calibration work for the telescope. Sometimes the telescope isn't pointing exactly where you want it to. And so you have to create a model to say, okay, if it's pointing in this direction, the offset is going to be, you know, X and Y sort of thing. And then if it's pointing in a different direction, your offset's going to be different. So you have a model to do the best to predict that. Students that have been involved with Simon's array work over the last few years. So we have Xander Hagen, Jacob Nelson, and Michael Liu, who have all graduated. And then currently Luke Porter is working with me on this telescope pointing model. So in conclusion, while the observations of Simon's array has concluded, the telescopes are being repurposed for continuing cosmological studies, right? And this is one of the kind of the best things that can happen when you're done with a project, that the instrumentation that you're using is still going to be used and is still going to be used to do great science. So anyway. This is a picture of the Simon's Array collaboration. It is an amazing group of people, and I'm very grateful to be working with them. This is a picture of the most recent face-to-face meeting that we had at Berkeley. And with that, that is it. Thank you for your time and attention.
Q&A.
Yes.
I'll stand
Of
behind.
course.
Something really basic. I see you're all working on that telescope at 17,000 feet. So how's the oxygen?
Not good.
So what do you do? Take oxygen breaks or what?
We wear a tank.
You do?
Yeah, and then we have a cannula that goes into our nose that we're breathing. Yeah, so we're breathing oxygen. Yep. Yeah, there are some people who, right, we have engineers who live there and they have acclimated. So they don't usually wear oxygen. They just, yeah, they've lived there. They have lived there their whole lives and have worked on the mountain. So they have acclimated. But for those of us who just, pop in for a week or a month, we're definitely using oxygen. Yep.
What's the E and the D wave? Is that electromagnetic and magnetic field?
So it is related to that. They're named after that. Yes. So, right. So two kinds. It has to do with the directionality. Let's see. So when you're talking about electromagnetic waves, your electric field is curl free and your magnetic field is divergent free. And so the E and B mode polarization, the E mode is curl free polarization and the B mode is divergent free polarization. You can kind of like, if I were to draw it, there would be like lines that travel straight, whereas curl would be lines that go in a circle. Yeah. Sorry, I think. Yeah. I don't know. Yeah, sorry, it's probably
Sort of like this.
sort of. Yeah, I'm sorry. I'm trying to think of a better way to explain that. Or no, I know there's a lot of experts in the audience too, so if anyone has a way to explain it, please feel free to.
In general, what are you determining with all this science? I mean, I know you just went through a tremendous amount of explanation, but most of it's Greek to me, but in layman's terms, what is it we're trying to do with all this?
Trying to determine whether or not a period called inflation actually happened at the beginning of the universe. That's what it is.
Inflation being what?
The hyper expansion of space.
So you're trying to validate that?
Basically trying to say.
If that ever did happen?
Exactly, yes.
And nobody knows that, nobody has a pretty good understanding that that's what happened.
Well, we don't have the evidence. We don't have all the evidence for it. Yeah, exactly. No, great questions. Yes.
I have two questions. Where was the equipment designed and where was it manufactured?
So let's see. There's a combination of places. Some of it was UC Berkeley, some of it was UC San Diego, some of it was in Japan at KEK, High Energy Particle Lab. Some of it was at Cardiff, which is in Britain. Oh, Wales. I'm sorry, my apologies. And then also, oh shoot, is a Canadian, McGill University. Yeah, those are the main ones where all this stuff was built and designed. Yes.
I remember a few years back, there was some polarization experiment and people got very excited, but it turned out it was actually just dust. Is that the same thing that
Yes,
you mentioned?
that's exactly it.
Ah,
Okay, fun story there. So when I was an undergrad at Berkeley, I happened to go to this talk that was done by a faculty member who is actually part of this collaboration. I get to work with him now. And yeah, he was giving a talk on this discovery that was just announced. It's like, oh, we found the primordial beam modes. And yeah, it was just interesting to hear his thoughts and perspective on it. It turns out that that signal was actually just interstellar dust, and not the actual signal that they thought it was. But yeah, it's kind of neat how, for me, that kind of came around full circle, or I heard this talk from him and now I get to work with him, so.
So they were measuring it in a very different way than you are, is that what it is?
It would, let's see, my understanding is that they were measuring it in the same way, but they didn't account for the dust signals as best as they could. So, right, because what we measure is a combination of both the CMB and what we call galactic foregrounds. So contaminations in our signal that come, as we're just looking out in space. So whether it's from dust, so there are these other signals besides the CMB that we have to somehow filter out. And so it's just that filtering, I think, wasn't as adequate as it could have been. Does that make sense? Yes.
Is that the statistical noise that you were telling us about and that you corrected by adding 2 extra telescopes? The dust would be that?
Let's see, no, so the dust would be a different kind of noise. Yeah. Jerry, did you have?
Yes, the method you use to detect the signal in the superconducting resistor, is that the first time that this particular design or effect has been used for these measurements?
I don't believe so.
Because the first measurements, I forget the name of the first probe that looked at the.
Oh, Kobe?
What's that?
Was it Kobe?
Yeah, Kobe.
Oh, that was a long time ago.
It was a super heterodyne detector.
Yeah, no, so I don't think this is the first time that we've used this kind of technology. There are other experiments, so
I like this one better.
yeah. Yes, in the back.
Question, you had one slide up there where you were talking about things being stable within 2 hertz. Was that a rotation in the phase plate?
Yes.
All right,
Yes.
so you're modulating the signal you want, and then you demodulate it later to
Yes.
get rid of the noise. All
Yes.
right, I understand.
Yep.
So what sort of signal to noise ratio do you achieve at the end?
Oh, that is a great question. Unfortunately, I'm not able to call that up off the top of my head. Yeah, Tom.
Is this system PolarBear making a map like the Planck satellite did? That you guys are coming up with a pattern of temperatures that like Planck did, or?
Yeah, no, so we're not making a full sky map. No, we're just looking at a small section. Yeah, so yeah, Planck did a full sky map. Let's see. I think typically, typically your ground-based telescopes will only be able to look at a section.
Yeah.
So,
The Earth's in the way.
yeah, exactly. Yes,
So you're basically trying to measure inflation, right?
evidence for inflation,
Evidence for
yes.
inflation. Preliminary results, do you have any preliminary results, yes or no kind of thing?
I think there is an inclination to say yes, because we think we have 2 of the 3 evidences that we would expect, but still need that 3rd one. So yeah.
Now, when they found the Higgs boson, I know you're not particle physics, but they needed 6 sigma certainty. And you had a 3.6 certainty, I think, at one point.
Right, one of the results was a 3.1, I think, yeah.
Do you have the same requirement of 6 sigma in your field?
That's a great question. For some reason, the 5 sigma stands out to me.
Okay.
Yeah, but grain of salt with that one.
Okay.
So what causes that anisotropy in the angular view of the sky?
Right, yeah, so let's see. So you mean the temperature anisotropies, right? So that's because there were areas of more or less gravity. And so you have denser areas and less dense areas. So when you have more dense areas, then you have a higher temperature, less dense areas, lower temperature.
Right, but what causes it to be on that particular scale? And why is it an angle and not a distance?
Let's see, right, so maybe to answer why it's on an angle and not a distance is because we're looking, I guess, we're looking at the like temperature fluctuations over a section of the sky. And so you can have sections of the sky where it's you have higher temperature variations, and then sections of the sky where you look over and there are lower temperature variations, I guess. Maybe I'm not sure what you mean when you say distance.
Well, that's all right. I'm just not understanding what, I mean, because, you know, you expect to see things being equal, and then when they send up Kobe, they saw that it wasn't all equal. But I didn't realize that there was this pattern to the anisotropy, and I was just wondering, is there any intuitive way to understand what causes that?
Right.
That pattern is frozen in quantum fluctuations from before inflation.
Right.
That's my understanding.
Yeah.
Okay.
Yeah, and then also like
No, before inflation?
Yes, when it was a single quantum particle that had, if it was,
Okay.
that had an insert, height.
Frozen at first light at 300,000 years. Or am I not understanding? The pattern that we're seeing, is it from that beginning, or is it frozen? I thought it was frozen at the 300,000 years.
So let's see, the pattern is evidence of inflation happening. So it would be the result of something from inflation that then is imprinted on the CMB. I don't know if that helps at all.
Yeah, we can only see back to 380,000.
I see, but you're saying
And
that.
inflation was way before that.
No, I was well aware of that, but so what you're saying is that even though we're only able to see 300,000 years, that is imprinted from the first microsecond or whatever it was
Hopefully.
before. But,
Hopefully.
Yeah.
okay. Okay, but you don't know what causes that particular frequency of the anisotropy.
Right, so let's see, there's the plot that I showed with the different peaks, and there
You
is
said it
a,
was about the angle of the diameter of the moon or something.
right, yeah, so on that
So
plot,
what is that?
it is fit to a model, a model that and I forget what all the different peaks mean, but each of those peaks represents a physical something that is a result of inflation, basically. Yeah.
Are you assuming then that as you move out in space a lot of distance, that you're going to have encounter evidences of this inflation? I mean, clearly there's a time element there, right? I mean, you're not examining this close in, you're examining this at a distance. Does that have a factor? Because theoretically, further you get away, the more primitive, you're looking back in time in terms of of when things happened, right?
Right.
So in order to measure what you're measuring, you need to be out there a ways in order to see that. Is that correct or not?
Right, so I think maybe I would say it depends on the well, let's see. I think right, because like, for example, with stars and galaxies, the farther away ones that we see, the older they are, right? Theoretically, yes.
That Webb is challenging a lot of that right now.
Sure, yeah. So yeah, with the CMB then oh, how do I say this?
The only time that she pointed out right at the beginning that the only time that you could get to thermal equilibrium was when the thing was still a quantum particle. Because it expanded so fast.
How do you find a quantum particle?
How do what?
How and where do you find a quantum particle?
Apparently at the beginning of our universe.
Yeah, but you don't see that, because that, I mean, if you've got to be in some sort of a place where you can capture that time. You're not so that
We can see back in time.
if you
And
go
because-
further and further away.
Yeah, and then, yes, but it's the whole sky. And if you go back 380,000 years after the inflation, then that's as far back as you can look. And so we see a pattern of things, and that pattern represents thermal variations. It was where the thing was very tightly one temperature, but the scale was 10⁻⁴ Kelvin.
Right.
For being variations. Those variations had to happen when the thing was a quantum particle. Because after that, immediately after that, everything was too far apart to talk to each other and come to equilibrium. So it's a good assumption that that pattern that you see in these cosmic microwave backgrounds, that it was actually, we're getting a look at what was inside that quantum particle. Provided our theories are right.
And I'm just trying to figure out, where are you looking? Close in or far away, or does it matter?
It doesn't
You're looking
matter.
at the whole universe.
You got a map of the whole universe, 104 pi radians of sky.
And at one point, everything was the same.
Yes, when it was a dot,
When it was a dot.
everything's the same.
Can I give you a question you might be able to answer?
Sure, that'd be great.
Every time I saw you pictured down in Chile with the
Yes.
device, you were outside in sunshine, sunlight.
At 17,000 feet.
I understand that, but
And
is it put inside a housing? Do you have an observatory over it?
Nope.
It's outdoors?
Yep.
At 3 miles up.
Yep. Sorry?
It's snow.
It
Is it snow?
it snows. Yep. So yeah, no, that is something was, weatherproofing the enclosure that holds the receiver on the telescope was also part of an engineering project to try and figure out how best to build an enclosure that protects it from the elements. Yeah.
Is it, go answer the question here. Go ahead.
The frequency of light, but that's a combination of the temperature and the velocity. Because of the Doppler effect. And if it was going way faster, the temperature would be lower. These are radio frequencies. You're measuring the frequency of light and that's spectrum, and that's a combination of the temperature of the black body and the velocity that's coming.
No, the frequency he's measuring is a spatial frequency of the structure. It's a size, that's why.
Yeah.
you have
Well,
to
you're
look
talking
at
about
there.
frequency, there's a difference between particles. You know what you're saying?
No, it's the difference between different parts of the pattern, how far apart they are.
Yeah, but the temperature you see in each of those parts is a function of the temperature and the velocity of that part. If it were traveling farther away,
It's just
it might be
temperature.
different. The temperature you see is gonna be a combination of the velocity and the block frequency you see will be a combination of velocity and the temperature, so it seemed like it would be hard to figure out what you're measuring.
Well, you better read the chapter because the test is this weekend. Before we go, Tom Cotton, are you in charge of running all these or is she up here?
I'm sending things out in Zoom, yes.
Is it possible to go back and pick up that big round oval map of the sky that shows the model?
Yeah.
Because I've seen that for years and I've wondered what the hell it is and what it represents, and I'd like to once and all fight.
Small variations in temperature.
Well, I understand that. I just have some basic questions about, there it is. Does that oval represent the whole night sky?
360, 4 pi radians.
So it's similar to the maps of the world that are
Yes.
laid out on flat,
Yes.
where Asia's over here and
Exactly.
we're over here.
Yes.
Why wouldn't it be a square or a rectangle? Why is
Are you a flat earther?
the earth flat? Because there's no way to fold that into a sphere.
Why would you want to pull it? Yeah, you could
But-
wrap it around it.
All right, what do the colors mean?
Temperature variation.
I understand that. Tell me what blue is.
Colder.
Colder. Okay, and the yellow represents warmer. If you were to superimpose the night sky that we know it, would it be on various places up there? Would we have the Big Dipper and the big
Yeah.
Orion's belt?
So
Would
let's
we have
see.
the constellations laid over it somehow?
If I had,
Yes.
woo, there we go.
What?
can show you that in the planetarium next month.
Do it.
CMB over the sky.
Do it,
Okay.
do it, do it.
Christy Cook, everybody.
There are maps that show you where the galactic plane are on here.
I've been seeing this map
So,
forever and I
yeah.
finally got just two colors, warm and cold.
Pat, I'm sorry? No, it's from Planck. So you had Kobe and then W map and then Planck. Sorry, Planck. Pat.
There are four folks down here, I think who had questions.
Okay.
Between Jerry and Michael, there was a interaction going on and their questions got kind of.
Oh, sorry about that.
Somebody take the floor, start,
Ben.
go for it.
So you mentioned that you were on an angular scale over there. Are those measured in seradians?
Those are measured, okay, those are measured in in L. So, have you talked about spherical harmonics yet in class? Okay, okay, I'm at a loss here. I'm not sure how to explain this. Anyone else know a good way of explaining spherical harmonics in L modes?
I can check the textbook.
Yeah, no, I'll teach you on Monday. We'll do that. We'll do a lecture on spherical harmonics. Yeah.
Where did the name PolarBear come from?
Ah, that's a great question. I asked that same question, and it was kind of funny because my advisor just very casually said something that kind of felt like he came up with it on the spot. No, so I think the lore is that polar comes from measuring polarization, and bear is because this was first developed at UC Berkeley, and their mascot is the golden bear. So there you have it.
Any other questions? Well, there's two things to do then before we go. Number one, clean out Jerry's Halloween candy as you're leaving. Everybody
Nice.
take one or two.
Yes.
We used to have a whole table right here for the years past covered with food.
That's
So
fun.
we used to end our meetings, boy, with socializing and eating.
Oh, great.
And the museum finally said, no, we're tired of the rats.
Yeah.
But I have I got something for you, madam.
Oh, what?
Your honorarium is inside our official ancient Chumash pristine porcelain cup.
Oh my goodness. Thank you so much.
Can I tell you a secret though?
Yes, in the microphone.
Well, I've been told that if you decline it,
Ah.
I can throw in our incredible bag. So you don't want this, do you?
Oh.
Tell me you don't want it.
Oh.
Say, I decline, okay? Bring down she didn't want it, so we're gonna give her all of it. It's like playing Let's Make a Deal with Monty Hall. Or Bob Barker with, come on down.
Oh,
And
thank
she is at
you.
Westmont, and
So
she'll carry this to class and
Oh,
here we are.
yeah, no, definitely. Thank you.
Jennifer
Really-
Ito, thank you. Everybody. Mr. President, would you like to close the meeting? We can socialize.
Thank you, Jennifer. That was an interesting project and an excellent presentation. And I apologize for interrupting you.
No, not at all.